Taken enough classes from me to know that that's not going to happen, right? All right. Well, let's go over a couple of announcements. Your next homework assignment is due on Friday. And if I'm not mistaken, you've just turned in your reservoir design. Phase 3 complete. So you've done phase 1, and maybe you've already updated your demand estimation, hopefully. Because if you haven't updated your demand estimation, then that's going to mean you have to redesign your pipe networks to reflect the new flow rates, right? So maybe you've even updated your pipe sizing based on the feedback I gave you there. You size the reservoir. So really the only thing that you have to do for that final project report submission is the cost analysis part of the project, where you're assigning, based on the number of linear meters of each pipe size you've used, you're assigning the cost to that, and you're extrapolating the price of your reservoir based on the given reservoir pricing data that's there. So how much does it cost is the last remaining question. And of course, if your write-up for phase 1 was handwritten, then probably you'll need to spend some time polishing things up for the final submission, because the final submission should be a typed document that is something you could share with a prospective employer. You know, think of it as a portfolio item where you're trying to show off, you know, this is how smart I can be. This is how good my calculations can look. This is how clear a communicator I am. You should hire me because I'm capable of things like this. And so the people who do that are going to get a really nice high grade on the final project report. And the people who just join together the draft submission for phase 1, 2, and 3 probably won't do as well. What I'm looking for is that you close the loop, that any issues that I've identified in the previous phases have been settled. And I'll go back through and refamiliarize myself, like what were the problems the first time around, so that I can look to see if those problems were addressed. And in your final report, it would also be great if you yourself talk about the evolution of the design. You know, if you say, well, at first my reservoir wasn't high enough on the hill, the pressures were too low, I was using the same pipe size for every element in the network. You know, just kind of go through what was the thought process, what were the parameters you were juggling. Just kind of explain, you know, what was this hydraulic optimization that you went through in order to arrive at the design that we're now seeing in the final PDFs. So just kind of lay it out for me. The history of your thinking is one interesting part of what you've gone through so far. All right, so I'm going to be looking over the spreadsheets and let you know what I think about your reservoir sizing. I'll probably wait to do that until after grading the exams, though. So any questions on the announcements before we move on?
On our final report, would you rather have multiple Excel spreadsheets, or would you like us to combine everything into one?
Spreadsheets with what?
Like different files with our calculations on them, or would?
Well, you don't necessarily have to have your calculations in the spreadsheet, except for the reservoir sizing. You know, a lot of people, I think, went with hand calculations, and that remains totally fine for the final project report. So, you know, if you used one spreadsheet for demand estimation and another for the reservoir sizing, separate files is fine. But what I'll probably spend the most time looking at is what I assume will be a PDF file or a .docx file, you know, like a Word document where that's your report, and I'm going to look at the drawings again. And I mean, I've already been through your calculations in the draft phase, and so if I have some remaining questions, I might look through your calculations again, or if I'm checking to see what changes were made. But some people, if their calculations were good the first time around, I won't revisit those a second time. Other questions? All right. We're talking about hydraulic jumps today, and I love hydraulic jumps. It's super interesting, especially because they're so useful out in the real world. Just to refresh your memory about what we were talking on Friday, that recorded lecture introduced a momentum depth diagram. And the first thing I mentioned with that is that this is different from the specific energy diagram you've seen before. The specific energy diagram, which you used to calculate alternate depths, is different from conjugate depths. A conjugate depth is talking about two different depths that has the same momentum. Whereas before, earlier when we were doing specific energy analysis, those two depths on a specific energy diagram have the same amount of specific energy. Here, the downstream depth in a hydraulic jump has way less energy than the upstream depth. Tons of energy is lost through that rapid transition. There's turbulence, there's entrained air, there's countercurrent flow, there are eddies. There's a lot of energy that gets dissipated in a hydraulic jump. So we wouldn't be able to use a specific energy diagram to predict anything with a hydraulic jump. But the interesting thing is that although energy is not conserved through a hydraulic jump, momentum is conserved through a hydraulic jump. And so that's what this diagram is saying, is that you can calculate the momentum function. M stands for the momentum function, and it's the sum of a parameter that's related to the area multiplied by the depth of the centroid. And then this term is a parameter that's related to the kinetic energy in the water. And so there's two different depths that have the same amount of momentum. Now, what I introduced in Friday's class was the Bellinger momentum equation. That's this one. It irritates me that you can't see that y2. It's y2 in the numerator of that. And so did we see a couple of different versions of the Bellinger momentum equation? We did. One in terms of the Froude number, another in terms of the ratio of the critical depth to the upstream depth. And I think in that video I pointed out that if you're using the Froude number version, you're squaring the upstream Froude number, whereas if you're using the ratio of the critical depth and the upstream depth, it's cubed. But with this Bellinger momentum equation, we can predict what will be the hydraulic jump's sequent depth. And so the water is moving supercritical. Why does the water go through a hydraulic jump? It's because this slope can't support supercritical flow. There's something that caused the water to go supercritical, and then it can't stay going supercritical anymore because maybe this is a mild slope. And you have to have a steep slope to support supercritical flow. So you've got this fast-moving water that has no right to be flowing at supercritical conditions. It just maybe water was coming from an underflow gate. That's how we induce supercritical flow in our lab, is we've got this gate which is pinching down, and then the water comes out supercritical, and then it goes through this jump and back to the normal depth. So the channel that's downstream of the hydraulic jump, there's a certain depth that the water will be going when conditions are steady and uniform. Well, once the water came out from this gate, the flow here isn't steady and uniform because we've got an obstruction in the way that changed the flow conditions. So the water is coming out at this supercritical flow, and it can't stay supercritical because the slope itself only supports a subcritical normal depth. So there has to be this transition. And water can't go through a smooth transition from supercritical to subcritical. It has to go through a rapid transition. And that's what the hydraulic jump is. All right, so what I'd like to do is have you get some experience and practice using the Bellinger momentum equation to find, for this case, if we have a rectangular channel that's 9.4 meters wide, it's a big channel, and it's carrying 123 cubic meters per second, and we know the upstream depth before the hydraulic jump is 0.86 meters, what will be the downstream depth after it goes through the transition? Okay, so what you'll need to do is calculate the Froude number upstream. So where it says FR1, that means the Froude number upstream of the hydraulic jump. Find the Froude number, substitute it into the Bellinger momentum equation, and find y2. And then the second part of this example, it's asking, find the fraction of the initial energy that is lost through the jump. So it's saying E1 is what? And then you're finding delta E1 is how much energy is lost. And so the fraction of the initial energy, so fraction of initial is the delta E divided by E1. Now E has the same meaning that it did previously. E is still the depth plus the velocity head. So find out how much energy was there before the hydraulic jump occurred, and then the fraction of the initial energy that's lost through the jump. So here's the loss relative to the initial energy, and that'll just illustrate how these hydraulic jumps are useful for dissipating energy that otherwise could cause damage to the stream bed. Like if it was earthen stream bed, or it has the potential to cause scour because the water's moving so fast, you can force the hydraulic jump to dissipate some of that energy at a controlled location before it causes damage downstream. Okay, so I'm going to pause for a second, give you a chance to calculate the Froude number, y2, and then we'll see if we can predict what the downstream depth will be. Okay, so on this one, I calculated the initial upstream velocity, 15.2 meters per second. Calculated the flow per unit width, although you don't necessarily need that to calculate the Froude number, because here you can see it calculated in terms of the flow per unit width, or if we don't bother with that and just calculate it based on the full uppercase Q, you get the same thing. Our Froude number is 5.238. So the Froude number is greater than 1, meaning supercritical flow. And this particular channel has a subcritical slope. So it can't support supercritical flow. So it's necessary that the fluids are going to go through a transition. We got our Froude number, substituted into the Bellinger momentum equation, and the downstream depth should be 5.956 meters. So tons of energy is being dissipated here. If you think that it initially was flowing at 0.86 and then it went up to 5.956 meters. So we could also find the sequent depth by constructing a specific energy diagram. That would be another approach. You know, setting up a table similar to what we saw from the recording on Friday, where if we set up a table that had flow rate, width of the channel, and then a variety of different depths and corresponding depth to the centroid, corresponding area, velocity, and so on. If we did that, if we created a momentum depth diagram and we found out for the depth that we're interested in, this depth of 0.86, if we were going to use this table approach, we'd put in our depth of 0.86, find out how much momentum function there is, and then do goal seek and try and find what is another depth that has that same amount of momentum. So that would be another approach to calculating the sequent depth downstream after the jump. But this problem-solving approach works just fine, 5.956 meters. Now, what about the second part of the question? Find the fraction of the initial energy that's lost through the jump. Okay, so the initial energy that we had is the depth and velocity head. And the energy loss, here's our formula for the energy loss. So 6.456 meters of energy is lost through the transition. And the initial energy was 12.659. So as a fraction, it's 0.51, meaning that the hydraulic jump is dissipating 51% of the specific energy that existed before the jump. So the jump itself is getting rid of some energy that otherwise could cause scour and damage to the material in the channel downstream. So it's pretty common for when dams are being designed, if they know there's going to be an overflow spillway. Let me just go back to the picture of the dam that we looked at last week, the Grand Coulee Dam. Okay. So in the vicinity downstream, it's common for them to put in features that force a hydraulic jump, because you want it to happen at a location of your choosing rather than the hydraulic jump form downstream where maybe you haven't armored the bottom of the channel. And so it could be that they have placed concrete some distance downstream of the spillway. It's common to put in big blocks of concrete so that the water flows into those blocks of concrete, and then as it begins to lose energy through contact with those concrete blocks, then it forces a hydraulic jump in the region close to the spillway. Because there's just so much energy that gets picked up as the water is flowing down the front face of the spillway that if you allowed that energy to exist down here, it would begin to scour the stream. All right, so any questions on this calculation example? Well, let's review trapezoidal geometry, because we've just done an example with a rectangular channel. And so calculating the depth of the centroid is pretty easy. If it's a rectangular channel, it's just the depth of the centroid is the flow depth divided by 2. But if you have a trapezoidal channel, it's a little bit trickier because the channel is more wide at the top than it is at the bottom. All right, so what I would like you to do here is think about, for a channel that has a bottom width of 3 meters, and you can see it's got 1-to-1 side slopes on both sides. So first of all, what is the top width?
5.
Good. How'd you know it's 5?
The 1-to-1 slope and the ones.
Okay. So if we've got 1 meter of depth, then that means that the length on the corner is a meter. The top, I guess we'd say the top width that's associated with that triangular section. So we've got the 3 meter bottom width and then an extra 1 meter on either side. So capital B is 5. All right. Now, there's also this formula I dug up that says the distance from the bottom upward to the centroid for a trapezoid is this. So delta H is a little bit different. Delta H measures from the water surface downward. So in this example, what I'm going to ask you to do is find out for this trapezoidal channel, what's the distance from the bottom of the channel up to the centroid, and then subtract that distance from an overall depth of 1 meter to find H bar. So H bar is the depth minus the distance up from the bottom to the centroid. So in other words, it's what's left over from the depth. Okay, so this is important in case you ever have a hydraulic jump in a rectangular channel and you need to factor in the depth of the centroid when constructing the momentum function. So we'll work through this example. So if this is rectangular, then the depth of the centroid would just be 0.5. But because we've got extra area at the top that isn't at the bottom, that takes the average location of the center of area higher than the midpoint. Okay, so distance up to the centroid, thus the H bar is 0.4583. Okay, any questions about that illustration, which, remember, the significance of the depth of the centroid is if you go through the process of calculating the momentum function, then you need to know h bar for that. Oh, it looks like here is that hypothetical I was talking about, like 123 cubic meters per second. Is that the right example? 9.4 meter. Yeah, 9.4 meter width. We have the depth of 0.86. So here's the depth of 0.86. We find the equivalent momentum 194. So if we have the 5.956 that we calculated with the Bellinger momentum equation, this just kind of is a proof that shows it has the same amount of momentum, 194 cubic meters. Strange units for momentum, but for this momentum function, those are the units that we're keeping track of. All right, so any questions about this trapezoidal geometry review? So if you had a problem where you were asked to draw a momentum depth diagram for a trapezoidal channel, you'd be able to do that. All right. One important aspect of hydraulic jumps is where they form relative to the things that cause them. You know, I was showing you the picture of the Grand Coulee Dam, and I was explaining that they try to force the hydraulic jump to occur in a certain location that they've engineered to absorb the impact of all that energy being dissipated. And so hydraulic jumps on their own can have a pretty long run before they set up. And by run, I mean the distance away from the thing that's causing the hydraulic jump. So here in this illustration, this is an underflow gate that's causing the hydraulic jump. And just to show you a couple of things, the dashed line represents the critical depth. And so you can see that what happened was the gate impinges on the flow of the water, and there was pooling upstream of the gate. But since the opening of the gate is lower than the critical depth, that's forcing the water to come out of the gate at a depth that's less than the critical. And that's another way that we know flow conditions are supercritical, is by definition, if Y1 is less than YC, you've got supercritical flow. But this mild slope, mild is a technical definition. That technically means a slope that cannot support supercritical flow. So when conditions are steady and uniform in this mild slope, the downstream depth, the normal depth, is going to be subcritical. So ideally, what happens is that the capacity of the channel downstream causes the downstream normal depth to be exactly the same as the sequent depth out of the hydraulic jump. And maybe to understand like why that's ideal, you have to see a non-ideal case. So this is ideal. What makes it ideal is that y prime 1, and here by y prime 1, what this means on this slide is the sequent depth that occurred after the hydraulic jump. So this is a little confusing, and it's unfortunate our book does it this way. But you know the Bellinger momentum equation? It says y2 for the downstream depth, right? So now, when we talk about the location of the hydraulic jump, y prime 1 is the downstream jump, the downstream depth after the jump. And then when they say y2, that's referring to the normal depth that's supported by the channel. So this warning, new variable definitions. Our textbook throws us that curveball there when it starts talking about hydraulic jump locations. But you know, all of these terms are defined here. Now, a rating curve is something that describes the relationship between the depth and the flow rate. So let me show you an illustration of a rating curve. So on the horizontal axis is flow rate, and on the vertical axis is depth. And so what makes this ideal is that the rating curve, both of them are on top of each other. That's saying that for a certain flow rate, you need to have a certain depth, and They correspond exactly in an ideal case. In other words, the ideal case is the one where the hydraulic jump occurs immediately. Now, non-ideal, look at the difference in the profile. This jump happened immediately after the contraction concluded. There's a little bit of a period where the water's still accelerating after it comes out of the gate. Because of the force that's behind it, it continues to accelerate, so that's why the depth is tapering. And then as soon as it's done accelerating, it jumps. Now, in contrast, a downstream depth jump is where there's this long period of gradual varying flow where the depth is getting a little bit higher, and then the rapidly varying flow of the hydraulic jump. Now, what happens in this downstream jump is that if we look at it from the tailwater rating curve, so here's the rating curves. The tailwater rating curve says that for a certain flow rate, less of a depth is needed compared to the hydraulic jump. So in other words, there's some normal depth downstream. So in this downstream jump, this example, if it was the same width of channel and the same flow rate, the slope is steeper. Because the slope is steeper, Y2 is less. And so remember that in a hydraulic jump, the water has to find its sequent depth. If I go back to a momentum depth diagram, the water can only jump from one depth to its sequent. And so if the normal depth downstream is some sequent depth, you have to wait until you get to the corresponding upstream sequent depth for the jump to occur. So the way to understand this, this downstream jump is that here in this one, the normal depth just happened to equal the sequent of the upstream depth. But if it was steeper, Y2 here is less because it's a steeper slope. So Manning's equation says that the normal depth is going to be less. And the hydraulic jump occurs when this gradually increasing depth finally matches up to the sequent of the downstream depth. So it couldn't jump yet at this point. It couldn't jump because its sequent wasn't available downstream. The water depth was increasing until finally it matched up with what the sequent would be in the normal period, in the section that's flowing with normal uniform flow. So that occurs when the tailwater rating curve is more efficient than the hydraulic jump rating curve. In other words, the channel can carry the flow really easily so that it doesn't need to be as deep. Because the channel is steeper, the water depth doesn't have to be as deep for a certain flow rate. Yep.
To fix that, or to make the hydraulic jump occur closer to the gate, would you be able to raise Y1 a little bit?
Yes, that would do it. Yep. So the things like when we're in the lab, the things that we can do to change where the jump occurs is, number one, that flume in the lab has an adjustable slope. So if I make it steeper, then that is going to make Y2 shallower. And so if I make it steep, the jump will run away from the underflow gate. But Seth is right. If you open the underflow gate, then this is going to be less supercritical than it was before. And so if it's less supercritical than it was before, it's going to be jumping up to a shallower depth. In other words, if we go back to a momentum depth diagram, if you have a really shallow depth, it's going to go through a huge transition to find its sequent. But if the depth isn't as shallow, upstream of the jump, it's not going to need as deep a sequent. So the closer the two depths are to the critical, the less the jump height itself is. This is really abstract stuff, and just hearing it this one time I'm explaining it to you, in 99% of the cases, isn't going to be enough to understand and remember it. So even if you're not in the habit of reading the textbook, I would strongly encourage you to read this section of the book, because it'll help you to understand and internalize a little bit more about hydraulic jumps and like why a jump would run away from the gate or why a jump approaches the gate. So here, when it's approaching the gate, the issue is that the tailwater rating curve is less efficient than the hydraulic jump rating curve. So if we look at the tailwater rating curve, it's above the jump rating curve, meaning that for a certain flow rate, it's going to take a larger depth. So in other words, the hydraulic jump becomes drowned. The jump is submerged, and you actually kind of don't see it when you have a case like this. An upstream jump, the water in the tailwater is pooling because it's not a very efficient channel. And so even though the gate is relatively low here and we've got water coming out supercritical, the channel downstream isn't able to convey it out of the way, and so there's a submerged jump. So the characteristic there is that the jump rating curve is below the tailwater rating curve. So just to think of it another way, here's the Bellinger momentum equation. In this illustration, we've got a really shallow Y1. And so think about this formula. If you have a small Y1, like very small Y1, that's going to give you a big Froude number because it's very supercritical for a certain flow rate. So if you've got a big Y1, if you've got a big Froude number, then that's going to mean that Y2 is large. So in other words, in this hypothetical momentum depth diagram, we can tell that the critical depth is the point of minimum momentum function. So it looks like approximately the critical depth, if each one of these is, let's see, 0.5, 0.6, 0.7, 0.8, 0.9, and 1. Okay, so here is that approximately 0.8 is the critical depth here. Now if Y1 is 0.6, so if we had an actual depth of 0.6, then its sequent to that is over here at a depth of about 1.05. So if Y1 is pretty close to the critical depth, so if with a Y1 of 0.6 and the critical depth of 0.8, then it's going to have a relatively small jump height. But if you have a initial upstream depth that's far from the critical depth, so 0.3, see the length of this distance between the two sections on the momentum function diagram, that is how high the jump is going. So that's the difference in elevation between Y1 and Y2. So here, the difference in elevation between Y1 and Y2 is small. Here, the difference in elevation between Y1 and Y2 is big because we were more supercritical when the depth is 0.3. And the bigger the jump, the more energy that gets lost through the transition. There's different types of jumps that are classified based on their initial Froude number, upstream. An undular jump is one that has a Froude number from 1 to 1.7. And as we look at these different jump types, it's important for you to take a look at these typical flow patterns. And the flow patterns that interact with the bottom of the channel are considered relatively undesirable. Because what we don't want is we don't want a lot of pressure coming down from above to the bottom of the channel and stirring up the stream bed. You know, if it's gravel, if it's sand, or even if it's concrete lined, a lot of movement of the water down and interacting with that bottom of the bed can cause scour. So with an undular jump of a Froude number from 1 to 1.7, that basically means there's not much of a change in depth. A weak jump would have from 1.7 to 2.5, and you'll notice that these flow vectors aren't interacting with the bottom of the channel, which is good, but we're not dissipating very much energy in a weak jump. Oscillating jumps from 2.5 to 4.5 dissipate more energy, but there's a lot of erosion to the banks, and there's a lot of interaction with the bottom of the channel, so they're considered kind of destructive. The sweet spot, when you're using hydraulic jumps intentionally in the vicinity of hydraulic structures to dissipate energy, is a stable jump from 4.5 Froude number to 9. And the advantage with that is that you're dissipating a lot of energy, you're causing a big rise in the flow depth downstream, and you'll notice that the velocity vectors aren't coming to the bottom of the channel at all. So the ratio between the downstream and the upstream depth varies from 5.9 to 12. So there's a pretty dramatic change in elevation. And beyond that, if you have a Froude number of greater than 1, it's a rough jump, and again, there is so much energy that's being dissipated when you've got a Froude number above 9 that it would generally require concrete armored stilling basins and a lot of careful attention to what the channel is paved or lined with to prevent it from getting scoured downstream. When we get together on Wednesday, we're going to talk about some formulas that exist to help us calculate how long a hydraulic jump is, and then we'll go into the lab on Wednesday and we'll look at some hydraulic jumps and take some measurements. So I will see you then.